Welcome to the best explanation of special relativity you've ever wanted, part 2. So, in the previous video, I've talked about the first two principles of relativity and how Einstein established relative motion. Then we actually, derived a theory of space and time. We got a better understanding and comprehension of the reality of space and time according to Einstein. So how do we know that's the reality? What evidence do we have for that? I'll give a couple evidences. I'll give you one that you could actually do yourself. Let's say we're going to talk about a galvanometer. Galvanometer. So let's say we have different colors here. Get copper wire. Say we get a copper wire. You actually get a guitar string. Literally, if you got a guitar string lying around, maybe a copper one or whatever metal it is made of, you make a solenoid. Make a solenoid. And that's really just, let me make this a little bit bigger. Look something more like this. We get ourselves a solenoid, and maybe we can get a water bottle. We can wrap it around a water bottle. We can cut each end right here. Let's say we cut each end off right here, and then get our guitar string. Have the loose ends right here, and then inside of this solenoid, we're gonna have a string hanging from the bottle like this. And then we're going to get two magnets. We'll get two magnets, maybe one like this and one like this. And the string is going to be in between the magnet, like this. And then we're going to have a little piece of paper that we can fold up into a small little arrow. Maybe something like this. And right here, what we have right here is a compass. It's a compass. If you can put this in the magnetic field, it'll deflect, it'll actually turn and change its direction, and it'll point to, let's say, north, magnetic north. So we got our solenoid. It's just a copper wire in a loop, and if you run an electricity through it, it'll create a magnetic field. And that's all I'm trying to show right here. Exactly what I'm trying to show right here. So we're going to get our magnet. Let's take this color right here. We're going to get our copper string, or our guitar string. We're going to put a magnet. We're going to touch each end to the magnet. So to the battery. Battery's touching each end of the guitar string. The guitar string's in a loop, and it makes it to a solenoid. And what's going to happen is we're going to see the compass turn. The compass is going to deflect, is what they say. Like it's going to change its direction. Maybe it'll go this way or that way, and then whenever you remove the battery, it'll stop turning. Really, whenever you put the battery on, it'll turn to one direction. It'll pretty much be stuck there until you remove the battery. From an experiment that I've seen. And what you call this is called Ersted's law. Ersted's law. Ersted's law. You call that an electromagnet. It's an electromagnet. Now I'm gonna ask you a question, and I want you to pause the video and attempt to explain to me, without Einstein, classically, how do you explain this? How do you explain this? How does this happen? How does this happen like this? How is it possible? And now that you've actually paused and thought about it, if you have, let me show you. It works by Einstein. According to Einstein, let me clear this. If we look at our guitar string here, we're going to zoom in on a section of our guitar string. And let's say we have our electrons. Let's say we have our protons. protons. So classically speaking, in this wire, in a guitar string, there's it's neutral. The number of electrons to protons is the same. There's no really reason whenever you run the battery through the wire, there's no charge that should be there. There should be no force. The number of electrons is equal to the number of protons. The densities of the electrons are the same to the protons. But according to Einstein, there's length contraction. As the electrons move, let's say to the right, they accelerate. Length contracts. Density of protons becomes greater than the electrons, as I've explained in a previous video that you should go watch. That I recommend you go and watch. And so what we get here is we get a charge imbalance. It's actually a force. And according to Maxwell, in quantum physicists, whenever we get an electron or a proton, as it's at rest, there's an electric field that's generated. The electric field is just existing everywhere, ubiquitous in outer space. Everywhere is your space, surrounding from this source proton or electron as it's at rest. And as it accelerates, that same exact electric field is there, except now it's weaker. It's the same exact thing. It's the same particle, same field. It's just weaker. As it accelerates, it's weaker. They call that the magnetic field. The magnetic field is the electric field, and it's just a weaker version. And as the speed or the motion of the proton or electron speeds up, the stronger that field becomes. So essentially, electrons, electric field and magnetic field are the same thing. And so from that, as the electrons are stationary in space and as they move around in space, as it is in reality everywhere pretty much, there's electric field and magnetic field everywhere coupled together. I guess you can say coupled is the word I like saying. They're everywhere. So basically, you don't call it the electric field, you don't call it the magnetic field, you can really just call it the electromagnetic field. So what's going on here is, with that original solenoid, that galvanometer, with the galvanometer, what's happening is, the wire, as it's a solenoid is just, if you run a battery through the wire in a loop, or in a wire in general, or I guess a wire in a loop, it'll create a magnetic field. So as the wire is creating a magnetic field, it's interacting with the magnet hanging from the strength magnetic field, and it turns it, it deflects it. And that's working according to Einstein. That's how that works. It's just simply put, so complicated. I don't mean to complicate it. I guess you could say dumb it down a little bit. What's going on is, according to Einstein, as things speed up, length contracts, there's a charge imbalance, different densities of the charges in the wire. It makes a magnetic field that interacts with the magnetic field of the permanent magnet that's hanging from the string, and it deflects it. It's electromagnet. It's an evidence you can see for yourself. There's other evidences, let's say, what they call muons. I'll give you another evidence. If you got a more precise enough clock, let's say you got a clock, you can sort of do this experiment yourself. If you got a good enough clock and you got a plane ticket that you can buy, you get your clock, and it's precise enough. And you got two of these clocks. You can put it one on the surface of the Earth, and you could get another one. You go take a plane trip way high in the sky and come back, and you'll see that they're not in sync. They're out of sync. They don't read the same time after the plane trip. That's because of time dilation, according to Einstein. And there's another evidence. Let's say high in the atmosphere, there's what you call muons that come down from the air. They come down from the sky. I guess maybe from radioactive decay of stuff in the sky. Not sure exactly behind the science behind all that. There's little tiny elementary particles that come down, raining down towards the surface of the Earth. And theoretical, the theory, scientific theory behind, how many of these particles should be coming down, given, sort of conditions in the sky, way up there in the atmosphere. Given those conditions, how many particles should you see raining down on the surface of the Earth for some elapsed time? And given that number that's calculated under the theory, it doesn't match what's actually experimentally observed according to scientists. They observe more. They observe more of these muons coming down. That's just indication, let's say, as you speed up, because these muons are going very fast, very, maybe some high percent of the speed of light, relatively speaking. If they're going fast like that, their time is being dilated, so they're aging more slowly. They're aging more slowly. Or aging more quickly, I might have that mixed up. I always get those confused. I know if you go high in the sky and outer space, I think you age quicker. So yeah, so these muons they're aging quicker. Uh, which means, basically, I guess you can say, they're in the future, and in the future they should have more particles in that future because, there's just, if you figure some elapsed time, there's going to have a lot more particles happening like that. So as more and more particles are accumulating, I guess you can say, they're going to come in now with more greater in numbers from time dilation. And that's some evidences of special relativity. You could also say GPS. There's GPS. There's like maybe I forget, maybe like four sets of 3 satellites or something like that in outer space. They're orbiting the Earth. So let me draw the Earth. Yeah, Einstein. GPS works with Einstein. What scientists say. We have Earth, all Earth. We got these satellites. Satellites out in outer space, and it's making our GPS work. And we use our Maps app to get from Alabama to Albuquerque. We use GPS and these satellites. These satellites, they work according because to Einstein, for one, I believe they have to make adjustments. They have to calculate because of their speeding, their time dilates, and they're high up. So according to relativity, general relativity, uh, they have a slower time, or I guess you could say their time is dilated. And they have to make corrections for this, for these facts. And in fact, the corrections they make match, let's say, the time dilation formula that Einstein provides in special relativity. Let's say T prime is equal to C times the gamma factor. And whatever corrections they make because of that, they have to get them all in sync with the clocks down here on Earth. The clocks on the satellites, to be in sync with the clocks down here on Earth, you have to use this formula, which you can derive using pretty much just Pythagorean theorem, very simple geometry and algebra. You can derive this formula right here, time dilation formula of special relativity. Using this formula and whatever formulas they have in general relativity, which I'm not too familiar with, that's really more of a PhD sort of education. Special relativity is more of bachelor's, maybe even master's, but general relativity, when you're dealing with gravity, is actually more of a PhD thing. And I'll touch on it a little bit in this video, actually. Maybe in another video I'll talk a little bit more. But these scientists and I guess engineers, they make corrections for the clocks that these satellites have, just so they can be, their time can match the same time that we have down here on Earth 5 o'clock. And that's some evidences of relativity, special relativity. Okay, so let's talk a little bit about E equals mc squared, relativistic energy. When you have something that's at rest, so you're at rest, this is Jim here, Jim, he's at rest, and some light's leaving him. Light leaves his body. So as he's at rest, let's say at moment 1, time t equals 0. Moment 0, time equals 0. Jim has some kinetic energy, and really it's just 0. His kinetic energy is just 0. And the light that leaves his body has some energy. So really, the total energy he has is just E. Right here, the energy of the light beforehand. This is going to be equal to his total energy. Let's put the sum of all energies. He has sum being the net energy. This is the sigma symbol for sum. So at moment zero, at t equals zero, Jim has some energy right here. And then if we was to compare with a different situation, let's say Jim, he speeds up. Now he has some speed. Now he has some non-zero kinetic energy. And then the light that leaves his body also has some energy. But the light that leaves his body, let's say in this case, after he has some velocity, isn't equal. According to Einstein, it's not equal to this E right here. It's a little bit different. A little bit different. It's going to be E times, let's say, I'm just going to make up this symbol for this adjustment factor, which is gamma, I guess you could say is what it's called. This is the Greek symbol for gamma, the capital Greek symbol. It'll be E times some adjustment factor. It's basically the energy of the light leaving his body after he's speeding up, after he has some speed. It's going to be a different amount of energy. I believe it's going to be a greater energy. It's a greater energy. And that's simply because time is dilating. As time is dilating, let's say we have our light waves, and then it's a different well actually that's not, let's see, we have a different scale right here. Let's say 0 to 5, and then here's our dilated time. Maybe it looks something like that. This is our dilated time right here. You can see the frequencies for the light, this light wave, are different. If you figure how many cycles per second, which is the hertz, the frequency of this light is different given the time is dilated for the moving thing. Given that's different, technically speaking, the energy is different. The energy is different. It's not really different. It's merely more of an apparent difference. It's more of an apparent difference, which I'm going to touch on that a little bit. Apparent being more an illusion. I think that's more of a definition. You can look up Google apparent, and maybe you'll find up it means an illusion. So if we get, let's say, kinetic energy plus E, energy of the light before, whenever you're at rest, then the kinetic energy plus E times gamma, that's an F. I didn't mean to put F there. What we can do is we can solve for the energy. You can maybe write half times mv squared for the kinetic energy right here. Half mv squared. And either case, you can consider you to be at rest. You consider Jim to be at rest. According to Einstein, that's relativity, the first two principles of relativistic motion. You can be considered to be at rest in either case. But in the second case, even when you're at rest, his time is dilated. And yet the light has a greater energy. It has some apparent greater energy. So where does this energy come from? Well, it turns out if you solve for E here, whenever you just do some rearranging of the equation, you'll get E is equal to mc squared. And all that's saying is the energy that we have, and that's given that the velocity is not considered to be changed, the masses would change. According to Einstein and relativity, velocity doesn't change. It's the same thing. It's the mass that must change. It must be the mass that changes. And we'll get this equation here, E equals mc squared. And so if we get our rest mass, given our rest mass, this is basically just saying the rest mass contains or has some sort of energy that is equal to mc squared. And the units work out, that's going to be kilogram meter per second squared, that's joules. Joules right there. And really that's just an apparent energy. The apparent energy gain is equal to some apparent mass gain. Basically, the way I explain that works is as space-time is changing, it's dilating, it's contracting, you're remaining inert in there. You're not really changing your velocity. You're not accelerating relative to other things that are at rest. Because of that, uh, there's an apparent energy gain. And I guess you can technically say that if you was to remain inert in changing space-time, you can actually appear to do work and make things accelerate just from your mass alone. If you can actually harness that energy from that mass, it's pretty much like making energy out of nothing. Uh, and another thing. Oh yeah, by the way, the E equals mc squared. I'm gonna get a little bit deeper. Really, the true equation is this right here. Remember that gamma factor that I talked about in a previous video? The gamma, which is just lowercase gamma. It is equal to 1 over the square root of 1 minus b squared over c squared. And you must put this gamma here. So this mass is the rest mass. If you speed up, the relativistic energy is a little bit different. A little bit different. Must be equal to mc squared times that gamma factor. And the higher your speed goes, the higher your energy is going to be, your relativistic energy. And this gamma factor also pops up, let's say, in the second law of motion that Newton gave. We get our second law of motion, which is just going to be the sum of our forces is equal to mass times acceleration. Yeah, sure, that's what Newton said, but according to Einstein, we have to change it a little bit. There's a revision. We should put a gamma there, meaning the faster you speed up, the greater the force is going to be experienced as you speed up. As your speed gains and gains higher and higher, the forces that's involved in acceleration they're harder. They're stronger and harder. So that's a little bit about special relativity. Now let's move on to general relativity, which is more of a PhD thing. It's a PhD thing. It's a little bit beyond me. According to Einstein, there's two principles that that's based off of also. I believe maybe, let's say the first principle of general relativity is, I guess to derive the field equation, Einstein's field equation, I guess to actually derive general relativity itself. The first principle, I think, is just that inertial mass is equal to gravitational mass, and then the second principle is, I think the speed of light can actually bend in a gravitational field. But from those two principles, you can really just derive general relativity. General relativity is precisely what it is, according to Einstein. It's the overarching idea of relativity. Special relativity is the special case. General relativity is saying, hey, there's curved space-time. There's space-time, and you can actually just move through it. Relative motion is inside of space-time. That's general relativity. Relative motion is inside of space-time, and it can be curved. Special relativity is the flat version of space-time and the relativity. General relativity is the overarching idea where space-time can be curved or it can be flat. It's both cases. And general relativity is basically saying, hey, the Earth and other things, people, particles, mass, I wouldn't necessarily say particles, but masses and things in general, they curve space and time around it. And things that are around the Earth, let's say Jim right here. Jim is right here. He's just remaining inert. He has a constant velocity, or he's not accelerating relative to the background stars or other things out there. He's not accelerating relative to it. He has a constant velocity through curved space-time. And that appears as gravity. It appears that he's accelerating. Really, as we're here on Earth, we're really the ones accelerating according to Einstein. And this person right here has a constant velocity relative to the background star. But to us, it appears we're at rest and he's accelerating. There's a kind of a demonstration you can do that's an analogy to demonstrate this sort of idea. Let's say you have a ball. Actually, I wanted to draw, actually take a picture of me demonstrating this myself. You get a ball. Just a simple demonstration. It's not too fancy, but let's say you get a stick, just a straight stick, and you shine some light at it toward the ball with a flashlight maybe, and the lights shining at the stick on the ball. There's going to be a curved shadow, a curved shadow on the ball. Let's see, one second. Get orange, yellow, show this in. And on the ball, they'll have a curved shadow. Yeah. And that's just an analogy for saying, hey, as we're on Earth, to stick to itself, it appears that it has a constant velocity. But here on Earth, it's actually accelerating, and it's actually moving with a curved motion. It really just has a constant speed through curved space-time. And it appears to be accelerating from here on Earth. In other words, what I'm basically saying is, as Earth curves space-time around it, time is curved. Time is bent out of place. So what that means is, a point in your future is below you as you're in free fall. If you're in free fall, let's say Jim's in free fall right here. The point in the future is below him. So he will, travel downward. He will free fall. That's just another way of looking at it. Really, space isn't really a curve as much. It's time that's mostly curved. So because of that, gravity exists. If you try to say, like, let's say that old analogy where you have these sort of dimples in space. You say maybe something's in orbit around these dimples, and sure, that's a good analogy, and I think it actually matches. It actually, the motion and all that actually matches what same sort of motion would happen if it was like a trampoline or something like that. But if you try to, look a little bit more deeper, if you just get something right here, put it right here, don't give it any motion this way or this way, just let it stay here stationary, and then let it go, then try to explain why is it going to accelerate downwards. You can't really explain it that way. The analogy doesn't really work in that case. To explain it more better, you have to say, hey, time is curved. A point in your future is below you, so you'll fall down. You'll have free fall. In other words, you have a constant velocity. You're not accelerating relative to background stars and galaxies, which are really what you call an inertial reference system, or they're not accelerating either. Just going off of special relativity. It's the overarching idea that there's space-time and there's relative motion. And I guess some other thing I guess you can say, I was talking about E equals mp squared is really just the apparent energy. Same thing with gravitational potential energy. Let's say here's the Earth. Here's the Earth. And let's say we grab a ball. We grab a ball and we give it some small force upward, a very small force, enough to accelerate it very slightly and give it some very slight energy. And then we give it the force up until the point that there's zero net force acting on it against gravity. Gravity plus whatever normal force you're applying to it, there's zero. You rise it up to some position above Earth's surface or some position above the center of the Earth. And now it apparently has ability to do work. It has the ability to accelerate downwards, but yeah, we didn't give it that much energy. We didn't give it really too much energy. So how is it possibly doing that? Well, that energy, that gravitational potential energy, is just an apparent energy. It's really like we're getting energy out of nowhere. It's like conservation of energy. Not really. It's just apparent energy. It's not. It's an illusion. What's going on is this ball has a constant velocity, or it's not accelerating, or it's inert relative to the background stars. And space-time is curved, and it has a constant velocity to curve space-time. And from our position here on Earth, we're accelerating, and the ball has a constant velocity. But it appears that we're not accelerating, we're at rest, and the ball is accelerating. So that gravitational potential energy that it has, it's an apparent energy. It's not really a violation of the law of conservation of energy. It's just an apparent illusionary energy. What else can I talk about? I think I did want to say some other things. What was it? Well, for the most part, that was pretty much what I wanted to cover as far as the topic of relativity in general, special or in general, specifically in specific cases or in the general case. That's relativity. When you think about relativistic motion, not really absolute motion, but relativistic motion, that's relativity. Another thing is, not everything is relative according to Einstein. That's not actually true. According to Einstein, motion is relative, but the laws of physics and the speed of light are absolute. And I guess now is a good time, which I maybe should have done in the beginning, is actually define what relative and absolute means. Well, I guess you could say absolute and objective are total opposites. You consider absolute, let's say objective. Objective means it's the same. Everything's the same. It's agreed upon to be the same relative to everybody. Whereas absolute means things are true and the same relative to nobody. Whether anybody exists or not, it's true regardless of that. Relativity is basically saying relative just means it's true because of people. Uh, Maybe not everybody is an objective whole, but maybe as a subjective sort of single person or thing. Things are personal. Things aren't really objective, they're not absolute, they are personal. Everything's personal as far as motion goes, according to Einstein. That's relativity. Einstein says motion is relative. Personal thing. And so is space and time. Space time is also relative, according to Einstein. What else did I want to say? There is one thing I want to say, but I want to try and remember what else I wanted to say before I say that last thing that I think I for sure want to end on. I know time can dilate in gravitational field. The closer you get to the gravitational body, uh, time dilates greater and greater and greater. Gravitational time dilation. Uh, if you were to go near a black hole, because of this, if you approach a black hole, time dilates so much that as you enter the black hole and as you approach it, you can watch the entire future of the universe unfold right in front of your eyes. The entire future. There's different sort of rates and scales of time going on with each case of me, you, and the surroundings. According to Einstein, time dilates as you approach massive bodies, and as you approach the black hole, this sort of time dilation would be a very crazy phenomenon. Can you imagine actually that happening going on as you approach it? Probably be scary. uh, what was the other thing I wanted to say? Well, if there's anything else, maybe I'll put in the description. But the very last thing I wanted to end on, and let me draw Einstein for a second. Let me draw Einstein for a second. I draw him yellow like the Simpsons. Here's Einstein. He has some brown eyes. Thanks. Yellow again. He has crazy silver gray hair. Last thing I want to say is a quote from Einstein himself. Einstein. Let's actually call him by his whole name, his first and last name, Albert Einstein. Albert Einstein said, his quote is, and I always tell this quote to people, the important thing to do is to never stop questioning. That's the important thing to do, never stop questioning. And when it comes to questioning, as a scientist or maybe as a boffin, I would rather really call myself, I don't want to be pretentious and actually try to make myself seem like I'm smarter than I really am. I found that, if you ask the right question, it can really work wonders. It'll really make you think, and you can actually really maybe come up with something really smart and important. It's really part of how the scientific method goes. You get an educated guess. That's the first step of the hypothesis. And the hypothesis, the first step of the scientific method, take an educated guess. Well, what's the guess to? It's to a question. It's an answer to a question. If you ask the right question and make an educated guess and follow the steps of the scientific method, you can actually possibly make a scientific law or scientific theory, maybe something important. And just really ask the right questions. And as a tutor, I'm actually a tutor. I tell my students to really think hard about the right question to ask me. If they have any question to ask me, and try to think of the best question to ask me so I can help them as best as I can. So just really work on questions and never stop asking questions, and think of good questions to ask. And until next time, I'll see you guys later. Bye bye.